Hello and welcome back to Calculus 1. Right, we have derivatives of exponential and logarithmic functions. And we start with the good old formula you already know, seen 5,000 times. The derivative of e to the x is e to the x. And then you had that chain rule formula, which was also, something that you memorized. The derivative of e to the ax is a e to the ax. And now that you know the chain rule, you know how that formula, became what it is. But you don't really need to memorize it anymore because now you know how to do the chain rule, right? Because this function, ax, the derivative of that is a, so times a. The question is, if I'm to use the chain rule now, what is the derivative of e to the f of x? Because I want to have e to the sine x, e to the cosine x, e to the x squared minus 1, and all of that kind of stuff. Well, we just use chain rule. We know that the derivative of e to the x is e to the x, so we write e to the f of x. And then we are multiplying by the derivative of f. Now this becomes the formula that is going to pretty much cover every single case that you're going to have in your calculus career. It's not the most general form, but it's the most frequent one out there. So like 95% of your exponential functions is going to be this derivative. What is the most general form? Well, clearly, it will be the derivative of whatever base raised to the function. Not just e. How about 2 to the sine x? Or 7 to the x squared minus 1, right? So now this b as a base could be any number, not just special number e. And the derivative of this will follow the same pattern. It's going to be b to the f of x times f prime of x, and here's the new piece, times ln b. So this is the most general case that you can get. Most of the time, you will be using the one in pink. Most of the problem, 95% of the problem, maybe even more, will be here. And you already know this because of the basic chain rule. However, the most general case is, yeah, I know most general, right? We don't use that, but this is actually a general case here because you can have any function in there. It's limited because this is always e as a base. So most general means you can vary b, you can vary functions. So yeah, it's more general than the one before. So looking at these formulas, if you have e to the sine x, as I mentioned before, in a derivative, you would have e to the sine x. Note, Control C, Control V, right? Copy and paste. So, and then times the derivative of the exponent, which is just cosine x. And you're done. We had this, we did this morning during the chain rule. So now we just want to focus on the new one, right? What is the derivative of, let's say, 6 raised to x squared plus 5? Well, if you follow the string, what is given to you up there, you see that this and this is the same. So just copy it. And then your exponent is f of x. Take the derivative of f of x. and then times ln b. You know that's a 6 because you can see it. So these derivatives are very quick. Exponential derivatives are the cheapest derivatives we have, with the least amount of thinking involved. Copy the same thing times the derivative of the exponent times the ln of the base. That's what it is. Copy the problem times the derivative of the exponent times ln of the base. And then you make it pretty. 2 ln 6 is a constant times x times 6 to the x squared plus 5. Note that I put the parentheses for 2 ln 6. I just wanted to make sure that that 6 is separated from x, so it doesn't look like it's a ln 6x. ln 6 times x is different than ln 6x. It's the same thing, right? Well, no, this is linear, and this is logarithmic. They are not the same. They will never be. Let me put that in blood over here. They don't even belong to the same type of functions. You have a linear, which is in polynomials, and logarithmic, which is in transcendental functions. So they don't even belong to the same realm of functions. Vastly different. One for you to practice. What is the derivative of 2 raised to the tangent x? Alright, so the rules are: copy as is the derivative of the exponent and times ln of the base. Done. Yay. That's all it is. So those are the derivative of exponential functions. Now we're getting to the part where we are going to deal with logarithmic functions. And generally, this story, for me at least, starts with talking about logs in general first. And then we do pre-calc, and then we do calc. Because I noticed that, you know, for a lot of students, logs are still not understood because you discriminate. So let's talk about it. Let's first do an exercise that covers a lot of math. 2 plus 3 is? Someone, please. And then I go 5 minus 2 is? And 5 minus 3 is? Yay, right? So this would be like the, you know, first grade, second grade, and so on. 2 times 3 is? And 6 divided by 2 is? And 6 divided by 3 is? Yay. So now I have addition, way to undo it. And then I have repeated addition, which is called multiplication, and the way to undo it. All right, let's go and do the exponents. 2 cubed is 8. Great. So cube root of 8 is 2. How do I retrieve 3? A log. Log base 2 of 8 is 3. That's where they fit. This is a basic operation. So why is log unfortunate? Because it's the only operation that you have over there that has letters instead of a cute symbol. Right? We have a plus and a minus. We have multiplication and division. Then we have these exponents and roots and things like that. And all of a sudden letters. And everyone goes, oh! Guys, it's a mathematical operation between two numbers. It's all it is. It's not a function, right? It's not a function by default. Just like none of these are functions by default. How do I make a function? I make a function when I say x plus 3. And that's a function now, linear. I make a function when I say 2x. Perfect, right? I make a function when I say 2 to the x. So I'm going to make a function when I say log 2 of x. Right? Logarithms are not functions. It's a way to compute a number. Now, the reason why you separate it from the pack is because it's learned so late that you don't actually connect it as a piece of, here, basic computation. Sure, these guys are terrible to compute on their own, right? I can also ask, hey, how's your long division, right? I can do that as well, knowing how much the calculator plays the role in everything. But in the end, log is just a way to combine 2 and 8 and get 3. Just like division combines 6 and 3 to give me 2. Bueno? So now that we understand that log is not this, you know, out of space thing, we define log function of some base, a or b, whatever, of x. And then we have the graph for log function, which gives you the domain and range and all of the other cool stuff. You can shift it up, down, left, right. You can do whatever you want. Reflect, right? All of that. So now, going further, I'm looking into the calculus of this, because clearly I can draw tangent lines all over the logarithm graph, so there has to be a derivative of a log. And there is. But before we get there, we are also going to do this special case first, right? So when you have log of base e of x, we write that as ln x. So what is ln x? ln x is a lazy notation for the full notation. It's 2 characters shorter, and it stands for logarithm natural, right, which is base e. E is the special number for exponents, so log e better be a special for logs, and then we denote that as ln x. So now you learn that ln x is not special. Just like log base 10 of x, we just call log x. So now on your calculator, you have a ln button, and you have the log button. That just means the base is e, or the base is 10. And you can take a look at your calculators, if you have them with you, and quickly find those buttons on the right-hand side, I mean left-hand side if you look at the calculator. Left-hand side, log, and below that ln, they're all the way by numbers 4 and 7. So now, as you are looking at this, you can go and you can compute logs. You can say log base 2 of 16 is, and you can use rules and things, right? It's going to be 4. So it's a way to combine these things. Now, one of the ways to compute this is to use the conversion formula that a to the b equals c is log a of c equals b. That's the conversion. So my problem, which was log 216, is equal to a question mark, which is x. I can convert that into 2 to the x is equal to 16, and I know that I can write 16 as 2 to the 4. So from there, x equals 4, which is the answer to the log question. So not as easy as saying 3 plus 8 is 11, clearly, but possible. When this nice factoring and things don't line up, you have the calculator to give you the decimals. The same like with division or anything, right? 12 divided by 6, yeah, it's 2. 12 divided by 7, eesh, right? So logs do the same thing. Certain logs you can calculate like this, right? And certain logs you punch in the calculator and calculate. So it's fine. So no complaints there. So now that we understand that these logs are not terrible, right? It's just a way to compute things, and they work differently than, right? But you definitely have the least amount of experience in working with them because it was learned, 10 years after you learned addition and subtraction, or even longer maybe. You practice logs a little bit, and then we finally get to this calculus part. What is the derivative of ln x? So the answer to that is simply 1 over x. That's it. Now I'm not going to box this one a lot because it's going to be rare to use that formula. The formula that is there 99% of the time is the next one, and that's the big one. Be ready to box this, leave some space around it, and get your colors. d dx of ln of a function. That's the one that it's there pretty much all the time. ln of sine x, ln of x squared, ln of whatever. And that is simply going to be f prime over f. It is literally cut and paste f of x in the denominator and put its derivative on top. The most important formula for logs, right here. And as easy as copy f of x as is, put its derivative on top. Copy f of x as is, put its derivative on top. That's that. So what is the derivative of ln of, let's say, sine x? You take your sine x as is and you put it down. The derivative of sine is cosine x. The answer is cotangent x. That's it. A question for you. What is the derivative of ln of x squared plus x minus 3? So I'm hoping you did simply copy the function as is, the derivative upstairs, that's it, done, walk away. It's as simple as that. So not as simple as e to the x, right? But this would be like the second in line, right, of being simple. And just one more formula for this, and the rest will be next class. Logarithmic differentiation, that's next class. Right now, the formula is for the most general case, because log A, log B, right, any base of any function. Remember that ln has e as a fixed base. ln, I have it here, right? Right there. ln has e as a fixed base. Now I say log b of f of x. So this is the most general case you can get. And the derivative of that is you have the same piece, f prime over f, and then there is ln b in denominator. One more thing, and that's that. So try the example. Oh, I forgot to put the derivative in front, guys. There's d dx over here. The derivative of this is, there we go. Terrible, 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 terrible. All right, there we go. So the derivative of log base 3 of cosine x, whatever. So we copy cosine x, we put its derivative negative sine x, and then in denominator times ln of 3, which is negative tangent x divided by ln 3. Very simple. For logarithmic differentiation, which we are going to cover next time we meet, please review these formulas and the way to expand logs, which is exercise done in pre-calculus 1. So we have that ln of xy is ln x plus ln y. Ln x over y is ln x minus ln y. And finally, ln x to the p is p ln x. These formulas are used to expand log expressions. And here's an example. If I have ln of x cubed square root of x, let's say square root of x plus 1, divided by, say, sine x, using the three formulas up there, I will write 3 ln x plus 1/2 ln x plus 1 minus ln sine x. This is the skill that you need to know and review for the next class. So, knowing those three pre-calculus log formulas and being able to do the pre-calculus 1 problem. These problems are in chapter 3 for the chili pepper book I referenced a few times. We have in a tutoring center and library by Blitzer. So chapter 3, I believe section 3. I think it's 3.3. Or 3.4. It's either 3.3 or 3.4, can't remember. It's been a year. So it's one of those two sections. You need to know how to expand exponential, not exponential, logarithmic functions. Bueno. All right. See you. Bye.